In this presentation we will discuss quasi-static processes and an ideal gas in the context of the first law of thermodynamics. We determine the heat exchanged between the gas and its surroundings and the pressure-volume work done on or by the gas. We start with the classification of quasi-static processes in an ideal gas based on the criteria fixing one of the thermodynamic or process variables during the process. We will see that some of the classes were already introduced in the presentation on the ideal gas law. The first class of the processes which we will discuss here is the quasi-static version of isothermal processes. In other words, first we consider such quasi-static processes in a given amount of ideal gas, where the temperature of the gas is constant during the process. Then we will discuss quasi-static isochoric processes in a given amount of ideal gas, that is where the volume of the gas is constant during the process. The next class which is considered here will be quasi-static isobaric processes in a given amount of ideal gas. This class represents the processes where the pressure of the gas is constant. The isothermal, isochoric and isobaric processes were also discussed in the previous presentation. Now we introduce a further class of thermodynamic processes, called adiabatic process. When we introduced the concept of thermodynamic system, we talked about adiabatic systems separated by an adiabatic wall from its surrounding. Such a wall prevents the exchange of energy in the form of heat between the system and the surroundings. Based on this scenario, we can talk about adiabatic processes, where there is no exchange of heat between the system and the surroundings. Then we will present quasi-static adiabatic processes in a given amount of ideal gas, that is a process without heat flux between the gas and its environment. The last class of thermodynamic processes which we will introduce here is called polytropic process. In such a process, there is an exchange of heat between the system and its surrounding, but the amount of heat absorbed or released by the system is proportional to the change in its temperature. In other words, we will present a quasi-static polytropic process of a given amount of ideal gas, where the specific heat capacity of the gas is constant. Finally, we will present Carnot cycle, which is the theoretical model of the operation cycle of a steam engine. Since this cycle is a sequence of two isothermal and two adiabatic processes, we will use all the results obtained in the discussions of these two classes of thermodynamic processes to describe the conversion of heat into mechanical work in the cycle. We have already seen how to apply the first law of thermodynamics for an ideal gas. Now we will examine the heat exchange in different thermodynamic processes for an ideal gas. All the state variables of an ideal gas, that is its pressure, volume, and temperature, change in general thermodynamic processes. However, if we assume that the process is quasi-static, then the state variables are still related by the equation of state for a given amount of ideal gas. In other words, the ideal gas law holds throughout the process, that is the pressure P of the gas times its volume V is equal to the amount N of the substance, times the gas constant R, times the absolute temperature T of the gas. In quasi-static processes, the equation of state for an ideal gas represents a constraint connecting the state variables to each other, and each state variable can be expressed in terms of the other two variables. In a general thermodynamic process, an ideal gas exchanges heat with the surroundings and does work on the surroundings, or the surroundings do work on the gas. In both cases, the state of the gas changes, therefore the internal energy and the enthalpy of the gas change as well. We have already studied the change in the state of an ideal gas in some important cases, where the state variables satisfy a given condition throughout the thermodynamic process. An isothermal process is such an important process, where the temperature of the gas is constant. Here are some examples as a reminder. Typical isothermal processes in nature are the melting of ice and the boiling of water, since the phase transitions take place at constant temperature. A refrigerator also works isothermally. Although a set of changes take place in the thermodynamic cycle of a refrigerator, the temperature inside remains constant. The first step of the operating cycle of Carnot heat engines is also an isothermal expansion of gas in the cylinder of the engine. An isobaric process is another important thermodynamic process, where the pressure of the gas is constant. Melting and boiling are also isobaric processes since the phase transitions of water take place at constant pressure. An isobaric process takes place in hot air balloons as well. When the gas in the balloon is heated, it increases its volume and keeps its pressure constant. A steam engine is also a typical example for such a process, where the water entering the boiler of a steam engine is heated to its boiling point, vaporized, and then the steam is superheated. All these processes take place isobarically in the engine. The third type of the important thermodynamic processes is an isochoric process, where the volume of the gas is constant. An obvious example from the real life is cooking in the pressure cooker. If its valve is still closed, then it keeps the pressure constant in the cooker. The working principle of constant volume calorimeters is also based on the isochoric change in the thermodynamic state of the substance placed in the sample chamber of the device. Another example is the diesel engine, where the last step in its operating cycle is an isochoric depressurization in the cylinder of the engine. We will examine the heat exchange in these types of processes, but we also introduce another one, called Adiabatic process, where the heat exchange between the system and the surrounding is forbidden. In nature, adiabatic cooling is the process where the humidification of air results in cloud formation. The operation of gas turbines can also be approximated as adiabatic expansion of the gas, where the hot combustion gas expanding through the turbine spins the rotating blades. In fire syringes, a rapid adiabatic compression of the air in its cylinder causes the temperature of the gas to rise rapidly, which ignites the material at the base of the cylinder, resulting in a bright flash. Let us start our study on the conversion of heat with a quasi-static isothermal process in an ideal gas. We can imagine a cylinder filled with an ideal gas and sealed by a moving piston. In the initial state of this thermodynamic system, the gas has the pressure P1, the volume V1, and the absolute temperature T as its initial state variables. The gas absorbs the amount Q of heat from the surroundings in a quasi-static process, and we assume that it will have an isothermal expansion, that is, its temperature remains constant. As a result, the gas will have the pressure P2 and the volume V2 in its final state, whereas its temperature is still equal to its initial temperature T. At the same time, the expanding gas does the pressure volume work W' on the surroundings by moving the piston. In the case of an isothermal process, the equation of state for a given amount of ideal gas reduces to Boyle's law, stating that the product P of the gas and its volume V is constant. For a given absolute temperature T, this constant is equal to the amount N of the substance, times the gas constant R, times the absolute temperature T. This law is represented by the parametric set of isotherms in the state space, where the parameter is the absolute temperature of the gas. These isotherms are rectangular hyperbolas in the pressure versus volume diagram. We can also see in the diagram how the state of the system evolves from its initial state with the pressure P1 and the volume V1 to its final state with the pressure P2 and the volume V2 along an isotherm for the given temperature T. Boyle's law provides the relationship between the state variables in the initial and the final states of the gas, telling that the pressure P1 times the volume V1 is equal to the pressure P2 times the volume V2, or the ratio of the pressure P1 to the pressure P2 is equal to the ratio of the volume V2 to the volume V1. The first law of thermodynamics states that the heat Q absorbed by the gas is equal to the change U2 minus U1 in its internal energy, minus the work W done on the gas, or plus the work W' done by the gas. Since the internal energy U of an ideal gas is given by its mass m times its specific heat capacity CV for a constant volume times its absolute temperature T, the internal energy is directly proportional to the absolute temperature. As a result, the internal energy of the ideal gas is the same in the initial and the final states of an isothermal process. That is, the internal energy U1 of the gas in its initial state is equal to its internal energy U2 in its final state. Since the change in the internal energy of the gas is zero in an isothermal process, the total amount of heat absorbed by the gas is converted into the pressure volume work done by the gas, that is, the heat Q is equal to the work W'. Then the heat Q and the pressure volume work W' are given by the integral of the pressure P of the gas with respect to the volume V from the initial volume V1 to the final volume V2. If we substitute the ideal gas law into the integral, then we obtain the amount N of substance, times the gas constant R, times the temperature T, times the integral of 1 over the volume V with respect to the volume V from the initial volume V1 to the final volume V2. By performing the integration, we obtain N times R times T, times the natural logarithm of the ratio of the final volume V2 to the initial volume V1. If we apply Boyle's law in the form expressed under the pressure versus volume diagram, then the Q heat and the work W' can be written as the amount N of substance, times the gas constant R, times the absolute temperature T, times the natural logarithm of the ratio of the initial pressure P1 to the final pressure P2. This result demonstrates that the heat Q absorbed and the work W' done by the gas are positive for the expansion of the gas, and negative for the compression of the gas. In the case of compression, the work W done on the gas is equal to minus W', and the gas releases the same amount of heat Q to the surroundings. The second type of thermodynamic process in an ideal gas is the isochoric process, where the volume of the gas is constant. Let us consider a closed container with the volume V, which is filled with an ideal gas. Let P1 and T1 denote the initial pressure and temperature of the gas, respectively. If the gas absorbs the amount Q of heat from the surroundings in a quasi-static process, then its temperature will increase. Since the gas is confined in the container with a fixed wall, it cannot expand and its pressure will increase as well. The final pressure and temperature of the gas are denoted by P2 and T2. In the case of isochoric processes, the equation of state for a given amount of ideal gas reduces to Gay-Lussac's law stating that the pressure P of the gas is directly proportional to the absolute temperature T of the gas. The proportionality constant is given by the amount N of the substance times the gas constant R, divided by the constant volume V of the gas, which can be written as the mass M times the specific gas constant Rs, divided by the volume V. This law is represented by the parametric set of isochors in the state space, where the parameter is the volume of the gas. These isochors are lines in the pressure versus temperature diagram. We can also see in the diagram how the state of the system evolves from its initial state with the pressure P1 and the temperature T1 to its final state with the pressure P2 and the temperature T2 along an isochor for the given volume V. Gay-Lussac's law provides the relationship between the state variables in the initial and the final states of the gas, telling that the ratio of the pressure P1 to the temperature T1 is equal to the ratio of the pressure P2 to the temperature T2. The slope of each isochor is inversely proportional to the volume V of the gas. We have already seen that the first law of thermodynamics applied for isochoric processes tells us that the heat absorbed by the gas increases the internal energy of the gas, since the gas does not do any pressure-volume work. As a result, the total amount of heat absorbed by the ideal gas increases the internal energy of the gas. That is, the heat Q is equal to the difference between the internal energy U2 of the gas in its final state and the internal energy U1 of the gas in its initial state. The internal energy U of a given amount of ideal gas is equal to the mass M of the gas, times its specific heat capacity CV measured in an isochoric process, times its absolute temperature T. By substituting this expression into the first law, we obtain the following expression: the mass M times the specific heat capacity CV, times the difference between the final temperature T2 of the gas and its initial temperature of T1. If we insert Gay-Lussac's law into this result, then we can write that the heat Q absorbed by the gas is equal to the ratio of the specific heat capacity CV of the gas for a constant volume to the specific gas constant Rs of the gas, times the volume V of the gas, times the difference between its final pressure P2 and its initial pressure P1. Now we can conclude that in an isochoric process, the heat absorbed by an ideal gas is directly proportional to the change in its temperature and its pressure. This result demonstrates that the heat Q absorbed by the gas is positive for heating, where both the temperature and the pressure of the gas increase. The heat Q is negative for cooling, where both the temperature and the pressure of the gas decrease. The third type of thermodynamic process in an ideal gas is the isobaric process, where the pressure of the gas is constant. As in the case of the isothermal process, we consider a cylinder filled with an ideal gas and sealed by a moving piston. In the initial state of this thermodynamic system, the gas has given absolute temperature, volume, and pressure denoted by T1, V1, and P respectively. If the gas absorbs the amount Q of heat from the surroundings in a quasi-static process, then it will expand and its temperature increases, whereas its pressure remains constant. As a result, the gas will have the temperature T2, the volume V2 in its final state, whereas its pressure is still equal to its initial pressure P. At the same time, the expanding gas does the pressure volume work W' on the surroundings by moving the piston. In the case of isobaric processes, the equation of state for a given amount of ideal gas reduces to Charles's law stating that the volume V of the gas is directly proportional to the absolute temperature T of the gas. The proportionality constant is given by the amount N of the substance times the gas constant R, divided by the constant pressure P of the gas, which can be also written as the mass M of the gas times its specific gas constant Rs, divided by the gas pressure P. This law is represented by the parametric set of isobars in the state space, where the parameter is the pressure of the gas. These isobars are lines in the volume versus temperature diagram. We can also see in the diagram how the state of the system evolves from its initial state with the volume V1 and temperature T1 to its final state with the volume V2 and the temperature T2 along an isobar for the given pressure P. Charles's law provides the relationship between the state variables in the initial and the final states of the gas, telling that the ratio of the volume V1 to the temperature T1 is equal to the ratio of the volume V2 to the temperature T2. The slope of each isobar is inversely proportional to the pressure P of the gas. We have already seen that the first law of thermodynamics applied for an isobaric process tells us that the heat Q absorbed by the gas is equal to the difference between the enthalpy H2 of the gas in its final state and the enthalpy H1 of the gas in its initial state, since no technical work is done at a constant pressure. Then the total amount of the heat absorbed by the gas increases the enthalpy of the gas, that is, the heat Q is equal to the difference between the enthalpy H2 and the enthalpy H1. The enthalpy of an ideal gas can be written as the mass m of the gas, times the specific heat capacity Cp of the gas for a constant pressure, times the absolute temperature T of the gas. By substituting this expression into the first law, we obtain the following expression: the mass m times the specific heat capacity Cp, times the difference between the final temperature T2 of the gas and its initial temperature T1. If we insert Charles's law into this result, we can write that the heat Q is equal to the ratio of the specific heat capacity Cp for a constant pressure to the specific gas constant Rs, times the pressure P of the gas, times the difference between its final volume V2 and its initial volume V1. Now we can conclude that in an isobaric process, the heat absorbed by an ideal gas is directly proportional to the change in its temperature and its volume. This result demonstrates that the heat Q absorbed by the gas is positive for heating, where both the temperature and the volume of the gas increase. The heat Q is negative for cooling, where both the temperature and the volume of the gas decrease. Now we introduce the concept of thermal efficiency, measuring the fraction of heat absorbed by a thermodynamic system that becomes useful work. We denote thermal efficiency by eta, and define it as the ratio of the work done by the system to the heat delivered to the system. Let us suppose that the working substance in the system is an ideal gas, the heat Q is delivered to the gas and the pressure volume work W' is done by the gas. Then the thermal efficiency eta of a thermodynamic process in the gas can be written as the ratio of the work W' done by the gas to the heat Q absorbed by the gas. For an isobaric process in an ideal gas, the heat Q absorbed by the gas is given by the ratio of the specific heat capacity Cp of the gas to its specific gas constant Rs, times the pressure P of the gas, times the difference between its final volume V2 and its initial volume V1. The pressure volume work W' done by the gas is equal to the pressure P times the difference between the volume V2 and the volume V1. By substituting these expressions into the definition of thermal efficiency, we can write eta as the specific gas constant Rs divided by the specific heat capacity Cp of the gas for a constant pressure. If we apply Meyer's relation stating that the difference between the specific heat capacity Cp of an ideal gas for a constant pressure and its specific heat capacity Cv for a constant volume is equal to its specific gas constant Rs, then we can express eta as the difference between Cp and Cv divided by Cp. By dividing both the numerator and the denominator of the fraction by Cv, we obtain an expression that depends only on the ratio of the heat capacities. We can introduce the heat capacity ratio or the adiabatic index of a substance as the ratio of its specific heat capacity Cp for a constant pressure to its specific heat capacity Cv for a constant volume. As its name indicates, this quantity is just the ratio of the heat capacity Cp for a given amount of substance measured at constant pressure, to its heat capacity Cv measured at a constant volume, since the mass of the substance cancels out in the fraction. Then we obtain that the thermal efficiency eta for an ideal gas in an isobaric process is equal to the ratio of gamma minus 1 to gamma. We note that the heat capacity ratio can be determined for any ideal gas in statistical mechanics. It can be shown that gamma is equal to 5/3 for a monatomic ideal gas, and 7/5 for a diatomic ideal gas. Since the air can be considered as a mixture of diatomic ideal gases, its adiabatic index is about 7/5. Then the thermal efficiency of an isobaric process in a thermodynamic system using air as a working substance is somewhat less than 30%. The last type of thermodynamic process is an ideal gas, which we discuss here is the adiabatic process. By definition, in an adiabatic process there is no heat exchange between the thermodynamic system and in the surroundings. Any thermodynamic process undergoing in a system can be considered as an adiabatic one, if the boundary of the system is an adiabatic wall preventing the exchange of heat between the two sides of the wall. In other words, an adiabatic process can take place in any system with thermal insulation reducing the heat flow to a large extent between the system and its environment. Here we can consider an thermally insulated cylinder filled with an ideal gas and sealed by a piston. Since perfect thermal insulation does not exist, we can only talk about an adiabatic approximation of the processes in thermally insulated systems. However, if the change in the state of the system occurs rapidly enough, there is no time for a considerable exchange of heat between the system and the surroundings. Then we can apply the adiabatic approximation, as in the case of fire syringes, where the compression of the air in the cylinder is so fast that the heat produced by the compression of air cannot escape, and ignites the material in the cylinder. However, such a process cannot be studied in the quasi-static approximation, since the air does not remain in thermodynamic equilibrium during the rapid change in its state. Instead, we consider an adiabatic compression in the thermally insulated cylinder, where the initial temperature, volume and pressure of the gas are denoted by T1, V1 and P1, respectively. If the gas is compressed in the cylinder by the moving piston, then the pressure volume work W can be done on the gas without the exchange of the heat Q between the thermally insulated cylinder and the surroundings. In the case of quasi-static adiabatic compression, the slowly moving piston compresses the gas and it changes its thermodynamic state. The final temperature, volume, and pressure of the gas are denoted by T2, V2 and P2, respectively, where the volume V1 is greater than the initial volume V2. The first law of thermodynamics applied for an ideal gas states that the internal energy U2 of the gas in its final state, minus its internal energy U1 in the initial state is equal to the heat Q absorbed by the gas plus the work W done on the gas. Since the heat exchange Q is zero in the adiabatic compression, the total work done on the gas increases the internal energy of the gas, that is the work W is equal to the difference U2 minus U1 in its internal energy. For a given amount of ideal gas, we can substitute the expression mass m of the gas, times its specific heat capacity Cv for a constant volume, times its absolute temperature T into the internal energy U of the gas in the right-hand side of the equation. Then the work W done on the gas and the change in its internal energy U can be written as the mass m times the heat capacity Cv, times the difference between the final temperature T2 of the gas and its initial temperature T1. Since the work W done on the gas is positive, the gas warms up in the adiabatic compression. In the case of adiabatic expansion, an ideal gas does pressure volume work which decreases its internal energy, and the gas cools down. If we apply the differential form of the first law of thermodynamics for an infinitesimal change in the state of an ideal gas, we can write that the differential of the heat Q absorbed or released by the gas is equal to the differential of its internal energy U, minus the infinitesimal pressure volume work W done on the gas. Here the pressure volume work is given by minus the pressure P of the gas, times the differential of its volume V. Since dQ vanishes in the adiabatic process, the first law tells us that the differential of the internal energy U, plus the product of the pressure P and the differential of the volume V vanishes. The infinitesimal change in the internal energy U for a given amount of ideal gas is equal to the mass m of the gas, times its specific heat capacity Cv for a constant volume, times the infinitesimal change in its absolute temperature T. The pressure P can also be expressed from the ideal gas law as the mass m of the gas times its specific gas constant Rs, times its absolute temperature T divided by its volume V. If we substitute Meyer's relation into this equation, then we obtain that the pressure P is equal to the mass m times the difference between the specific heat capacity Cp and Cv, times the absolute temperature T divided by the volume V. We can insert these expressions into the differential form of the first law, which gives the following equation. The mass m times the specific heat capacity Cv times the differential of the temperature T, plus the mass m times the difference between the specific heat capacities Cp and Cv, times the absolute temperature T, times the differential of the volume V divided by the volume V, is equal to 0. If we divide this equation by m times Cv times T, then we obtain the following expression. The differential of the temperature T divided by the temperature T, plus the heat capacity ratio gamma minus 1, times the differential of the volume V divided by the volume V, is equal to 0. By integrating this separable differential equation, we find that the natural logarithm of the absolute temperature T, plus gamma minus 1 times the natural logarithm of the volume V is constant. Then we can write that the natural logarithm of T times V to the power of gamma minus 1 is constant, which tells us that the absolute temperature T times the volume V to the power of gamma minus 1 is constant. Now we can apply the ideal gas law for a given amount of gas, stating that the pressure P of the gas times its volume V, is equal to the amount N of substance times the gas constant R, times the absolute temperature T of the gas. Since N times R is a constant for a given amount of ideal gas, we can express the volume V as a constant times T over P, and substitute it into the expression T times V to gamma minus 1, which is constant. Then we obtain a constant times T, times the ratio of T to P raised to the power of gamma minus 1. This gives a constant times T to gamma, divided by P to gamma minus 1. Since the left-hand side of the first equation is constant, we can conclude that the expression T to gamma divided by P to gamma minus 1 is constant. We can also express the absolute temperature T from the ideal gas law as a constant times the product of P and V, and substitute it into the expression T times V to gamma minus 1. Then we obtain a constant times P times V, times V to gamma minus 1. This gives a constant times P times V to gamma. Since the left-hand side of the first equation is constant, we can conclude that the product of P and V to gamma is constant. As a result, we have obtained the functional relations for the state variables of a given amount of ideal gas, when the gas changes its thermodynamic state in an adiabatic process. These three relations are known as Poisson's equations, where the first one states that the absolute temperature T of the gas times its volume V raised to the power of the adiabatic index gamma of the gas minus 1 is constant. The second one tells us that the absolute temperature T to gamma, times the pressure P of the gas raised to the power of 1 minus gamma is constant. The third one states that the pressure P times the volume V to gamma is constant. Sometimes only the third equation is called Poisson's equation in the textbooks on thermodynamics. When we derived these equations from the first law and the ideal gas law, the amount N of the species was absorbed into the constants in the right-hand side of these equations. If we change the amount of species, that is either the amount of the gas or the type of the gas, or both, then these constants will change as well. Since the adiabatic index for a given gas is just the heat capacity ratio of the gas, it also depends on what type of gas goes under in the adiabatic process. Therefore, Poisson's equations provide different functional relations for different amount and types of gases. As an example, we can show Poisson's equations for a monatomic gas that has a heat capacity ratio of 3/5. Then the exponent gamma minus 1 in its Poisson's equations is equal to 2/5. In the case of a diatomic gas, the adiabatic index is equal to 7/5. Thus we obtain different Poisson's equations for a diatomic gas, where gamma minus 1 is equal to 2/5. Poisson's equation describing the functional relation between the pressure and the volume of a given amount of ideal gas in an adiabatic process is represented by curves called adiabats in the pressure versus volume diagram. Let us compare the properties of adiabats and isotherms in the state space of an ideal gas. Boyle's law states that the product of the pressure P and the volume V of a given amount of ideal gas is constant in an isothermal process. We can express the pressure P from Boyle's law as some constant C divided by the volume V. Then the partial derivative of the pressure P with respect to the volume V at a constant temperature can be calculated by taking the derivative of the constant C over the volume V. This gives minus C over V squared, which is equal to minus the ratio of the pressure P to the volume V. In the case of an adiabatic process, Poisson's equation states that the pressure P of the gas times its volume V to the adiabatic index gamma is constant. If we express the pressure P from this equation, we obtain a constant C prime divided by the volume V to gamma. The partial derivative of the pressure P with respect to the volume V for an adiabatic process, that is for the vanishing transfer of the heat Q, is the derivative of C prime divided by the volume V to gamma. This gives minus gamma times C prime over V to gamma minus 1, which is equal to minus the adiabatic index gamma times the ratio of the pressure P to the volume V. If we compare this result with the expression obtained for the isothermal process, we can see that it is equal to gamma times the partial derivative of the pressure P with respect to the volume V at a constant temperature. It can be shown that the adiabatic index gamma is greater than 1 for any substance, not only for an ideal gas. As a result, the tangent of the pressure P as a function of the volume V is greater for an adiabatic process than for an isothermal process in the same thermodynamic state, which can be illustrated as follows. Here we can see the surface and the state space of an ideal gas representing the ideal gas law. The three-dimensional state space is spanned by the axes of the state variables pressure P, volume V and the absolute temperature T of the gas. In the pressure-volume temperature space, Boyle's law is represented by a set of isochors, which are the section of constant temperature planes with the surface of the ideal gas law. These isochors can be projected onto the pressure-volume diagram, where they form a family of rectangular hyperbolas. If we choose an arbitrary state on one of the isochors represented by the point P in the state space, that can also be projected onto the pressure-volume plane. In the pressure-volume temperature space, Poisson's equations are represented by adiabats over the surface of the ideal gas law. We plot only one adiabat passing through the point P, demonstrating that all the three state variables of the gas change in an adiabatic process, whereas Poisson's equations represent the constraints imposed on the values of the pressure, the volume, and the temperature of the gas. If we project the adiabat onto the pressure-volume plane, we can see two different curves passing through the point P. Here we can see a set of isochors with the thermodynamic state represented by the point P in the pressure-volume diagram for a given amount of ideal gas. We also plot an adiabat passing through the point P. The slope of the isochor in the state represented by the point P, that is the tangent of the curve in that point, is given by the partial derivative of the pressure P of the gas with respect to its volume V at a constant temperature. Similarly, the slope of the adiabat in the point P is determined by the partial derivative of the pressure P of the gas with respect to its volume V for a vanishing heat flux Q. As demonstrated above, the tangent of the adiabats are greater than the tangent of isotherms in the same state, or in the same point in the state space. Then we can conclude that the slope of adiabats are greater than the slope of isochors in the same state of the gas, that is in any point in the pressure-volume diagram of an ideal gas. We will finish the discussion on adiabatic processes with their application, which helps us to derive the formula for the speed of sound. We have seen that if an adiabatic process takes place in a given amount of ideal gas, then Poisson's equation holds, stating that the pressure P of the gas times its volume V to the adiabatic index gamma is constant. Since the volume of the gas can be expressed as its mass m divided by the density ρ, we can insert this ratio into the equation. Here the mass m and the adiabatic index are constant. Therefore we can divide the equation by m to gamma, and absorb it into the constant in the right-hand side. As a result, we can write that the pressure P of the gas times its density ρ to minus gamma is constant. Since the right-hand side of the equation is constant, the differential of P times ρ to minus gamma vanishes. If we apply Leibniz's rule for the differential in the left-hand side of the equation, then we can expand it as the differential of P times ρ to minus gamma times P, times ρ to minus 1 minus gamma, times the differential of ρ. By multiplying out ρ to minus gamma, we obtain ρ to minus gamma times the quantity of dP minus gamma times P times ρ to minus 1 times d ρ, which must vanish. Since ρ to minus gamma is not zero, the differential can only vanish if the terms in the parentheses vanish, that is dP minus gamma times the ratio of P to ρ times d ρ is equal to 0. This result can be summed up in the differential equation, stating that the adiabatic index gamma times the ratio of the pressure P to the density ρ is equal to the derivative of the pressure P with respect to the density ρ. By applying the chain rule, the derivative can be written as the derivative of the pressure P with respect to the volume V, times the derivative of the volume V with respect to the density ρ. Since the volume V of the gas is just the ratio of the mass m of the gas to its density ρ, we obtain minus the derivative of the pressure P with respect to the volume V, times the ratio of the mass m to the density ρ squared. This gives minus the derivative of the pressure P with respect to the volume V, times the ratio of the volume V to the density ρ. If we invert the derivative, we obtain the differential equation stating that 1 over the adiabatic index gamma times pressure P is equal to minus 1 over the volume V, times the derivative of the volume V with respect to the pressure P. In addition, we will use another expression to derive the speed of sound in adiabatic approximation. Since the ideal gas law states that the pressure P of the gas times its volume V is equal to its mass m times its specific gas constant Rs, times its absolute temperature, we can express the pressure P as m times Rs times the ratio of T to V. The right-hand side of the equation is equal to the gas constant Rs, times the density ρ, times the absolute temperature T, which gives the equation stating that the ratio of the pressure P to the density ρ is equal to the specific gas constant Rs times the absolute temperature T. As already mentioned, adiabatic processes are related to the measurement of the speed of the sound in ideal gases. While Newton assumed that the propagation of sound in the air is an isothermal process, Laplace argued that the process is adiabatic. Indeed, the changes in the pressure and the density of the gas during the propagation of the sound wave are fast enough to prevent the exchange of the heat between the volume elements of the gas at the wave front and the surrounding medium. Therefore, the adiabatic approximation provides a better description of the phenomenon. The result derived here can be used to determine the speed of sound in an ideal gas, if we introduce the adiabatic compressibility of substances. As we did for an ideal gas in an isothermal process, we can introduce the adiabatic compressibility of an ideal gas in an adiabatic process. The adiabatic compressibility kappa ad is defined by -1 over the volume V of the gas, times the partial derivative of the volume V with respect to the pressure P of the gas for the vanishing heat flow Q. Since the differential equation obtained above was derived for an adiabatic process, we can immediately write the adiabatic compressibility of an ideal gas as 1 over the adiabatic index gamma times the pressure P of the gas. We already defined the isothermal compressibility of an ideal gas by -1 over the volume V of the gas, times the partial derivative of its volume V with respect to its pressure P for a constant temperature. When we determined its value, we obtained 1 over its pressure P. Therefore, the adiabatic compressibility kappa ad can be written as the ratio of the isothermal compressibility kappa to the adiabatic index gamma. Since gamma is greater than 1, the adiabatic compressibility of an ideal gas is always smaller than its isothermal compressibility. Now we can express the speed of sound in terms of the adiabatic compressibility, where the square of the speed of sound Cs is defined by the partial derivative of the gas pressure P with respect to its density ρ for an adiabatic process. If we apply the differential equation derived from Poisson's equation, we can write the square of the speed of sound as gamma times the pressure P over the density ρ. This formula differs in the multiplicative factor gamma from the one derived by Newton for isothermal processes. Since the adiabatic index is greater than 1, the sound waves propagate faster in the adiabatic approximation than in the isothermal description. By substituting the expression obtained for the adiabatic compression into this equation, we obtain 1 over the adiabatic compression kappa ad times the density ρ for Cs squared. We can also apply the equation obtained from the ideal gas law, and write the square of the sound speed as the adiabatic index gamma, times the specific gas constant R, times the absolute temperature T of the gas. We have seen that different criteria hold for different types of thermodynamic processes in an ideal gas. However, there is one common criterion applied in each process presented before. Since the specific heat capacity of an ideal gas for a given pressure or volume does not depend on the temperature of the gas, it was regarded as constant. If we do not neglect the small amount of heat exchanged between the system and its surroundings due to its imperfect thermal insulation, then we can assume that it is proportional to the bulk mass of the system, and the small change in the temperature of the system. In other words, the heat Q absorbed by the substance of the system is equal to a constant C called the generalized specific heat capacity of the substance, times the mass m of the substance, times the increased delta T in its temperature. Such a process taking place in a thermodynamic system of a constant generalized specific heat capacity is called polytropic process. We can consider a cylinder filled with an ideal gas and sealed by a moving piston. In the initial state of the gas it has the absolute temperature T1, the volume V1 and the pressure P1. For a given amount of heat Q absorbed by the ideal gas with the mass m, its generalized specific heat capacity C determines the change in its temperature, and in turn, the whole polytropic process. Since the only criterion is the constancy of the generalized specific heat capacity, all the state variables of the ideal gas change as the warming gas expands in the quasi-static process, while it does the pressure volume work W' by moving the piston. Then the gas has the absolute temperature T2, the volume V2 and the pressure P2 in its final state, where both the final temperature and the final volume of the gas are greater than the initial values of the corresponding state variables. Besides the generalized specific heat capacity C, the polytropic index N is applied in the description of polytropic processes, which is defined by the ratio of the specific heat capacity Cp of the gas for a constant pressure minus the generalized specific heat capacity C, to the specific heat capacity Cv of the gas for a constant volume minus the generalized specific heat capacity C. The first law of thermodynamics states that the heat Q absorbed by the gas is equal to the difference between the internal energy U2 of the gas in the final state and its internal energy U1 in the initial state minus the work W done on the gas, or plus the work W' done by the gas. Since we study the conversion of energy in the case of an infinitesimal amount of heat, we apply the differential form of the law stating that the differential of the heat Q is equal to the differential of the internal energy U, minus the differential of the work W. The expanding gas does an infinitesimal amount of pressure volume work, and minus dW can be written as plus the instantaneous pressure P of the gas, times the infinitesimal change in its volume V. For a given amount of ideal gas, we can write that the infinitesimal amount of heat Q absorbed by the gas is equal to the generalized specific heat capacity C, times the mass m of the gas, times the infinitesimal change in its absolute temperature T. The infinitesimal change in its internal energy U is equal to its specific heat capacity Cv for a given volume, times the infinitesimal change in its absolute temperature T. We can also express the pressure P of the gas from the ideal gas law, which gives the mass m of the gas times its specific gas constant Rs times its absolute temperature T, divided by its volume V. By applying Meyer's relation, we can write that the pressure P is equal to the mass m times the difference between the specific heat capacity Cp and Cv, times the ratio of the absolute temperature T to the volume V. If we substitute these three equations into the first law, then we obtain the mass m times the generalized specific heat C times the differential of the absolute temperature T, minus the mass m times the specific heat Cv times the differential of the absolute temperature T, minus the mass m times the difference between the specific heat capacity Cp and Cv, times the absolute temperature T, times the ratio of the differential of the volume V to the volume V, is equal to 0. By dividing this equation by the expression Cv times T and regrouping its terms, we can write that Cv minus C, times the differential of T divided by T, plus Cp minus Cv, times the differential of V divided by V, is equal to 0. If we add and subtract the generalized specific heat C to the difference between the specific heat capacity Cp and Cv, we will have the quantity of Cp minus C, minus of the quantity of Cv minus C. The first term can be expressed as the polytropic index N, times Cv minus C, which allows us to multiply out Cv minus C from the right-hand side of the equation. This gives N minus 1, times Cv minus C, which can be substituted into the second term of the right-hand side of the first law. If we divide the equation by the expression Cv minus C, we obtain the equation stating that the differential of the absolute temperature T divided by the absolute temperature T, plus N minus 1 times the differential of the volume V divided by the volume V, is equal to 0. This equation is the same as the one derived from the first law for an adiabatic process. The only difference is that the polytropic index N appears in the equation instead of the adiabatic index gamma. By integrating this separable differential equation, we obtain the same solution as in the case of the adiabatic process, stating that the absolute temperature T times the volume V raised to N-1 is constant. In the discussion on the adiabatic process in an ideal gas, we applied the ideal gas law for a given amount of gas, stating that the pressure P of the gas times its volume V is equal to the mass m of the gas, times its specific gas constant Rs, times the absolute temperature T of the gas. By substituting the law into the solution obtained here, we can derive two other equations for the functional relations between the state variables of the gas, which are the same equation as Poisson's equations for the adiabatic process. We only need to replace the adiabatic index gamma with the polytropic index N in the equations. As a result, the following equations describe the functional relations between the state variables of a given amount of ideal gas, when the gas changes its thermodynamic state in a polytropic process. The first one states that the absolute temperature T of the gas times its volume V raised to the power of the polytropic index N of the gas minus 1 is constant. The second one tells us that the absolute temperature T to N, times the pressure P of the gas raised to the power of 1 minus N is constant. The last equation states that the pressure P times the volume V to N is constant. Since the generalized specific heat capacity C is an arbitrary constant, the polytropic index N has an arbitrary value as well. However, if we evaluate the functional relations between the state variables of the gas for given values of the specific heat capacity and the polytropic index, then we will obtain a set of special cases which we already know. By regarding the polytropic index N as a function of the generalized specific heat capacity C, we can evaluate N for different values of C and substitute it into the equations. First, we evaluate the polytropic index for vanishing generalized specific heat capacity, which gives the ratio of the specific capacity Cp for a constant pressure to the specific capacity Cv for a constant volume. That is, the polytropic index N is equal to the adiabatic index gamma. As a result, the functional relations become Poisson's equations obtained for adiabatic processes in an ideal gas. If we set the specific heat capacity C to the specific heat capacity Cp for a constant pressure, then the polytropic index vanishes. A substitution of the vanishing polytropic index into the first equation gives the relation stating that the absolute temperature T of the gas, times its volume V to -1 is constant. This equation can be written as the relation telling us that the ratio of the volume V to the absolute temperature T is constant, which is Charles's law. This law provides the functional relation between the temperature and the volume in an isobaric process, which is not surprising since the generalized specific heat capacity C describing the heat transport between the system and the surroundings is equal to the specific heat capacity Cp for a constant pressure. Indeed, If the polytropic index vanishes, then the second equation reduces to the expression stating that the pressure P of the gas is constant. Then the third equation becomes redundant, as it also reduces to the same equality stating that the pressure P is constant. We can also evaluate the polytropic index N for the specific heat capacity CV for a constant volume. Then the polytropic index diverges, and we can take the limit for N as it tends to infinity. If we raise the first equation to 1 over N, then we obtain the limit stating that the volume V is constant as N tends to infinity. This is the condition of an isochoric process, as we expected when the generalized specific heat capacity C is equal to CV. We can raise the second equation to 1 over N as well. Then the limit of this equation gives another equation stating that the absolute temperature T times the pressure P to -1 is constant. This equation can be written as the relation telling us that the ratio of the pressure P to the absolute temperature T is constant, which is Gay-Lussac's law. That is what we expect for an isochoric process. The third equation is redundant again. If we raise it to 1 over N and take its limit, then we obtain the condition stating that the volume V of the gas is constant. If we increase the generalized specific heat capacity C such that it tends to infinity, the limit of the polytropic index N still remains finite and becomes unity. Then the first equation immediately gives the condition stating that the absolute temperature T of the gas is constant. Here the second equation is redundant since it also gives the same condition for N equal to 1. The third equation reduces to Boyle's law stating that the product of the pressure P and the volume V of the gas is constant, which holds in an isothermal process. Then our conclusion is the following. A polytropic process in a given amount of ideal gas can be interpreted as a general case for the different types of thermodynamic processes presented before. In other words, these processes are special cases of the polytropic process for a given polytropic index. We have demonstrated that if the polytropic index N is equal to the adiabatic index, that is the generalized specific heat capacity vanishes, indicating that no exchange of heat takes place between the system and the surroundings, then we talk about an adiabatic process. If the polytropic index N vanishes, that is the generalized specific heat capacity is equal to the specific heat capacity Cp, indicating that the pressure is constant during the process, then we have an isobaric process. If the polytropic index N diverges and the generalized specific heat capacity is equal to the specific heat capacity Cv, indicating that the volume is constant during the process, then we talk about an isochoric process. Finally, if the polytropic index N is equal to 1, that is the generalized specific heat capacity diverges, indicating that we cannot talk about the change in the temperature of the gas during the process, then we have an isothermal process. Now we present the graphs of the functional relation between the state variables of an ideal gas in each type of thermodynamic process. These graphs also illustrate the properties of the polytropic process in different ranges of the polytropic index, which we enlist here as well. Let us start with the pressure versus volume diagram of a given amount of ideal gas in the thermodynamic state represented for a given pressure and volume by the point P in the state space. This functional relation is given by the equation stating that the pressure P of the gas times its volume V raised to the polytropic index N is constant. Any isobaric process with the vanishing polytropic index N is represented by an isobar in the diagram, which is a horizontal line passing through the point P as its intermediate state. If we increase the polytropic index by small steps from 0 to 1, we can deform the line into a rectangular hyperbola passing through the point P, which is an isotherm representing the functional relation between the pressure and the volume of an ideal gas in an isothermal process. By increasing the polytropic index N further, we can reach the value of the adiabatic index gamma, which is greater than 1 for an ideal gas. The adiabatic curve passing through the point P is steeper than the isothermal, as the functional relation shows, where the volume V has a greater exponent for adiabatic processes than isothermal ones. If we increase the polytropic index N to infinity, then the tangent to the curve in the pressure-volume plane becomes infinite as well. As a result, we reach the isochoric process represented by an isochor, which is a vertical line passing through the point P. In the next diagram, we plot the graphs of the functional relation between the pressure and the temperature of a given amount of ideal gas in the thermodynamic processes with the intermediate state represented by the point P. Here the functional relation for polytropic processes states that the absolute temperature T of the gas raised to N times its pressure P raised to 1 minus N is constant. The isobaric process with vanishing N is represented by an isobar, that is a horizontal line passing through the point P in the pressure versus temperature diagram. For N equal to 1, we will reach an isothermal process represented by an isotherm, that is a vertical line passing through the point P. If n is equal to the adiabatic index gamma, then we have an adiabatic process where the adiabat passing through the point P lies between the isotherm and the isochor in the diagram, since the isochor with a diverging polytropic index is a straight line passing through the origin and the point P in the pressure-temperature plane. The last diagram for the functional relations between the state variables of a given amount of ideal gas is the temperature-volume diagram with the intermediate state of the gas represented by the point P. Here the functional relation for a polytropic process states that the absolute temperature T of the gas times its volume V to 1 minus n is constant. The isobaric process with vanishing n is represented here by an isobar, that is a straight line crossing the origin and the point P. The horizontal line passing through the point P is an isotherm with n equal to 1, representing the isothermal process. For adiabatic process with n equal to gamma, we have an adiabat passing through the point P, which lies between the isotherm and the isochor, since the isochor with a divergent n is just a vertical line crossing the point P. Although the polytropic index n is defined as a function of the generalized specific heat capacity C, we can invert the definition and express C in terms of n. As a result, we obtain the ratio of n times Cv minus Cp to n minus 1. By multiplying out Cv, we have Cv times the ratio of n minus gamma to n minus 1. We can use this expression to plot C as a function of n, which gives a pair of rectangular hyperbolas with the horizontal axis crossing the axis of the generalized specific heat capacity at Cv and the vertical axis erected at n equal to 1. The hyperbola on the left-hand side approaches Cv as n tends to minus infinity, that is the process approaches the isochoric process in the limit. Then it crosses the axis of the generalized specific heat capacity at Cp indicating the isobaric process, and diverges as n tends to 1 in the regime of the isothermal process. The hyperbola on the right-hand side decreases to minus infinity as n tends to 1, which is again the regime of the isothermal process. Then it passes through the axis of the polytropic index at gamma, which represents the adiabatic process with vanishing C. Finally, it approaches Cv as n tends to infinity, that is the process approaches the isochoric process in the limit. Based on these graphs, we can classify the thermodynamic processes in a system, for example a given amount of ideal gas in the different ranges of the value of the polytropic index. Here we use the energy transfer ratio K defined by the derivative of the heat Q exchanged between the system and the surroundings to the work W' done by the system. For a polytropic process and an ideal gas, we will demonstrate that the energy transfer ratio can be written as the ratio of the adiabatic index gamma of the gas minus 1, to the adiabatic index gamma minus the polytropic index n. By definition, the sign of the energy transfer ratio K determines the direction of the heat flux and the work done by the gas relative to each other, describing the conversion of energy in the polytropic process. Since the adiabatic index gamma is greater than 1 for an ideal gas, the sign of K is determined by the condition whether the polytropic index n is greater or less than gamma. If K is positive, then the heat Q and the work W' have the same sign. A gas absorbing the heat Q does the work W' on the surroundings, while the work W' becomes negative for a gas releasing the heat Q. If K is negative, then the heat Q and the work W' have the opposite sign. For a gas absorbing the heat Q, the work W' becomes negative, that is the work is done on the gas, while a gas releasing the heat Q does the work W' on the surroundings. We start the classification with the range of negative polytropic indices. For n less than 0 the energy transfer ratio K is positive, and the gas absorbing the heat Q does a pressure volume work W' which is also positive. A polytropic process with a negative polytropic index can be applied to describe the thermodynamic process in an interstellar medium, which consists of molecular clouds in the state of quasi-hydrostatic equilibrium. Such clouds, heated by an external flux of energetic particles or photons at denser regions near the center, which are cooler than the more tenuous regions near the surface, provided the flux is nearly uniform throughout the cloud. As a result, these molecular clouds have an increase of temperature and decrease of pressure toward the surface, which can be modeled with the polytropic temperature-pressure equation with a negative polytropic index. If the polytropic index vanishes, then the generalized specific heat capacity C of the system is equal to its specific heat capacity Cp for a constant pressure, for which the energy transport ratio is still positive, and we talk about an isobaric process taking place in the system. If the polytropic index is greater than 0 and less than 1, then the energy transfer ratio K is still positive. That is the gas absorbing the heat Q does a positive pressure volume work W'. Such a process can take place in high-pressure pneumatic systems, where switch valves are applied to reduce the pressure of air in the circuit of expansion in supply tanks. If the heat Q absorbed by a given amount of air in a constant volume tank is large enough to raise the air temperature in the discharging process, then the heat exchange and the work done in the pneumatic circuit can be described by a polytropic process of an index n less than 1. If the polytropic index n is equal to 1, then the generalized specific heat capacity C diverges, the energy transfer ratio K is still positive, and we talk about an isothermal process taking place in the system. If the polytropic index is greater than 1 but less than the adiabatic index gamma, then the energy transfer ratio K is still positive. For a negative work W' done by the system, the work Q is also negative, that is, some heat is released by the system to the surroundings. A well-known example for such a process is the thermodynamic cycle of vacuum compression refrigerators. In the first stage of the refrigeration cycle, the refrigerant enters a compressor as a low-pressure vapor. The compressor compresses the refrigerant to a high-pressure vapor, doing the work minus W' on the working substance. As a result, the vapor becomes superheated. Once the refrigerant is compressed and heated, it leaves the compressor and enters the condensation stage of the cycle, flowing through a series of the S-shaped tubes in the condenser. Since cool air is blown across the tubes by a fan, the hot refrigerant releases the heat Q to the cooler air and changes its state to a high-pressure liquid. If the polytropic index n is equal to the adiabatic index gamma with vanishing generalized specific heat capacity C and energy transfer ratio K, then we have an adiabatic process, where there is no heat exchange between the system and the surroundings. For the polytropic index n greater than the adiabatic index gamma, the energy transfer ratio K becomes negative. As a result, if the heat is released by the system, that is Q is negative, then the work W' done by the system becomes positive. A typical example for such a process is the thermodynamic cycle in internal combustion engines, where the heat Q is released from a fuel and air mixture in the cylinder of the engine during combustion. The expanding combustion gases push the piston in the cylinder, producing the work W'. As a result, the engine partially converts the energy from the combustion to mechanical work, whereas some amount of energy is lost in the form of heat through the fixed wall of the cylinder separating the combustion chamber from the cooler surroundings. If the polytropic index n tends to infinity, that is, the generalized specific heat capacity C is equal to the specific heat capacity CV of the substance for a constant volume, then K tends to minus infinity and we approach the isochoric process in the limit, where no pressure volume work is done. This classification illustrates well how the value of the polytropic index determines the transformation of energy in a polytropic process. Therefore, it is useful to derive some relations between the state variables, the process variables, and the change in the state functions of the gas. Let us start with the heat Q exchanged between a given amount of ideal gas and its surroundings in a polytropic process. We have seen that the infinitesimal amount of heat Q absorbed or released by the gas in a polytropic process is directly proportional to the mass m of the gas and the infinitesimal change in the temperature T of the gas, and the proportionality constant is the generalized specific heat capacity C. If we express the absolute temperature T from the ideal gas law, we obtain the mass m times the general specific heat capacity C, times the differential of the ratio of the pressure P times the volume V to the mass m, times the specific gas constant Rs. This expression reduces to the ratio of C to Rs, times the differential of P times V. Here we can write C as Cv times the ratio of n minus gamma to the n-1, and use Meyer's relation stating that the specific gas constant Rs is equal to Cp minus Cv. If we divide both the numerator and the denominator by Cv, then we obtain 1 over gamma minus 1, times the ratio of n minus gamma to n-1, times the differential of the product of the pressure and the volume. We can eliminate either the pressure or the volume from the product. Let us start with the pressure. For a given amount of ideal gas in a polytropic process, we have the functional relation stating that the pressure P of the gas, times its volume V to the polytropic index n is equal to some constant C. We can express the pressure P from this equation as C times the volume V to minus n, and substitute it into the differential of P times V. Then we obtain the differential of C times V to 1 minus n, which gives C times 1 minus n, times V to minus n, times dV. Since C times V to minus n is equal to P, the differential of the product of the pressure P and the volume V can be written as 1 minus the polytropic index n, times the pressure P, times the differential of the volume V. By substituting this result into the equation for the differential of the heat Q, we obtain 1 over gamma minus 1, times the ratio of n minus gamma to n minus 1, times 1 minus n, times p times dv. If we simplify the expression, we can write dq as the ratio of n minus gamma to n minus 1, times the pressure P times the differential of the volume V. We can also express the volume V from the equation stating that the pressure P times the volume V to n is equal to the constant C for a given amount of ideal gas. Then the volume V can be written as some other constant C prime times the pressure P to minus 1 over n. By substituting this equation in the product of the pressure and the volume, we can write the differential of their product as the differential of C primes times P to the ratio of n minus 1 to n. This gives C prime times the ratio of n minus 1 to n, times P to minus 1 over n, times dP. Since the volume V is equal to C primes times the pressure P to minus 1 over n, we obtain the ratio of n minus 1 to n, times the volume V times the differential of the pressure P. If we substitute his result into the equation of the differential of the heat Q, then we can write dQ as 1 over gamma minus 1, times the ratio of n minus gamma to n minus 1, times the ratio of n minus 1 to n, times V dP. By simplifying this expression, we can express the differential of the heat Q as the ratio of n minus gamma to n times the quantity of gamma minus 1, times the volume V, times the differential of the pressure P. Based on these results, we can determine the infinitesimal pressure volume work, and the infinitesimal change in the internal energy and the enthalpy for an ideal gas in a polytropic process. Since the infinitesimal pressure volume work W done on the gas is given by minus the pressure P times the differential of the volume V, the substitution of the formula derived above gives minus the ratio of gamma minus 1 to gamma minus n, times the differential of the heat Q. The first law of thermodynamics states that the infinitesimal change in the internal energy U is equal to the sum of the infinitesimal amount of heat Q and the infinitesimal work W. If we substitute the expression obtained for dW into the law, then the infinitesimal change du in the internal energy can be written as the ratio of 1 minus n to gamma minus n, times dq. By using the definition of the enthalpy H, we can express its infinitesimal change as the differential of the sum of the internal energy U and the product of the pressure P and the volume V. Then dH is equal to du plus V times dP, plus P times dV. Since each term in the right-hand side is already expressed in terms of dQ, we can substitute those expressions into this equation. If we simplify the sum of these terms, we obtain the ratio of gamma times 1 minus n to gamma minus n, times dQ. Now we summarize the results derived here for the relations between the differentials of the state variables, the state functions and the process or path variables for a given amount of ideal gas in a polytropic process. We obtained that the derivative of the heat Q exchanged between the gas and its surroundings with respect to the volume V of the gas is directly proportional to the pressure P of the gas, where the proportionality constant is equal to the ratio of gamma minus n to gamma minus 1. We also showed that the derivative of the heat Q with respect to the pressure P is directly proportional to the volume V, where the proportionality constant is equal to the ratio of n minus gamma to n times the quantity of gamma minus 1. We express the infinitesimal pressure volume work W done on the gas in terms of the differential of the heat Q as well. Since the heat transfer is normally derived for the work done by and not on the gas, we give the infinitesimal pressure volume work W prime done by the gas here, which is equal to the ratio of gamma minus 1 to gamma minus n, times the infinitesimal amount of heat Q. Finally, we also demonstrated that the infinitesimal change in the internal energy U is equal to the ratio of 1 minus n to gamma minus n, times the infinitesimal amount of Q, and that the infinitesimal change in the enthalpy H is equal to the ratio of gamma times the quantity of 1 minus n to gamma minus n, times the infinitesimal amount of Q. Since the isothermal, the isobaric, the isochoric and the adiabatic processes are special cases of the polytropic process, these relations hold for all of them. If we substitute the value corresponding to a given process into the polytropic index n, then we obtain a set of the equations describing the relations between the differentials of the state variables, the state functions and the process variables for the given type of thermodynamic process. We can also determine the explicit formula for the work done on the gas by applying the functional relation between the pressure P and the volume V of a given amount of ideal gas in a polytropic process, which states that the pressure P times the volume V raised to the polytropic index n is equal to a constant C. If we express the pressure P from this relation, then we obtain C times the volume V to minus n. This equation can be substituted into the pressure volume work W done on the gas given by minus the integral of the pressure P with respect to the volume V from the initial volume V1 of the gas to its final volume V2. Then we have minus C times the integral of the volume V to minus N with respect to the volume V from the volume V1 to the volume V2. Here we have two cases for the polytropic index N. If N is not equal to 1, then the primitive function of the integral is equal to minus C times the volume V raised to 1 minus N, divided by 1 minus N. By evaluating the primitive function, we obtain the ratio of C to N minus 1, times the quantity of the volume V2 raised to 1 minus N, minus the volume V1 raised to 1 minus N. We can substitute the formula obtained for the pressure into this expression, which gives 1 over N minus 1, times the quantity of the final pressure P2 of the gas times its final volume V2, minus the initial pressure P1 of the gas times its initial volume V1. If N is equal to 1, then the primitive function is equal to the natural logarithm of the volume V. By evaluating the primitive function, we obtain minus C times the natural logarithm of the ratio of V2 to V1. Since N is equal to 1, the constant C can be determined by the ideal gas law, which gives the mass m of the gas times its specific gas constant Rs, times its absolute temperature T, times the natural logarithm of the ratio of the initial volume V1 to the final volume V2. This formula was already derived for the work done on an ideal gas in an isothermal process, which is a special case of the polytropic process, as we can see here. For the sake of completeness, the explicit formulae for the heat Q exchanged between the gas and its surroundings in the polytropic process is also presented here. In its infinitesimal form, dQ is given by the mass m of the gas times its generalized specific heat capacity C, times the infinitesimal change in the absolute temperature T of the gas. If we integrate this equation for the whole process, then the total amount of heat Q is equal to the mass m times the generalized specific heat capacity C, times the difference between the final absolute temperature T2 of the gas and its initial absolute temperature T1. We have already seen that the infinitesimal change in the internal energy U of a given amount of ideal gas is given by the mass m of the gas, times its specific heat capacity CV for a constant volume, times the infinitesimal change in the absolute temperature T of the gas. Then the change delta U in the internal energy for the whole process is equal to its integral, which is given by the mass m times the specific heat capacity CV, times the difference between the final absolute temperature T2 of the gas and its initial absolute temperature T1. We also determined the infinitesimal change in the enthalpy H of a given amount of ideal gas, and we found that it is equal to the mass m of the gas, times its specific heat capacity Cp for a constant pressure, times the infinitesimal change in the absolute temperature T of the gas. Then the change delta H in the enthalpy for the whole process is equal to its integral, which is given by the mass m times the specific heat capacity Cp, times the difference between the final absolute temperature T2 of the gas and its initial absolute temperature T1. Based on these relations, we can give a summary on the polytropic process in an ideal gas by presenting all of its special cases in this table. In the first column of the table we specify the type of the process for different values of the polytropic index N. In the second column we will show the condition describing the given process. The third column will contain all the functional relations between the state variables of the gas which hold for the given process. In the fourth, fifth, sixth and seventh columns, we will show the heat Q exchanged in the process, the work W done on the gas, the change delta U in the internal energy of the gas and the change delta H in the enthalpy of the gas respectively. We start with the polytropic process of an arbitrary polytropic index N, which is the general case of all the other thermodynamic processes presented before. The condition specifying the process states that the generalized specific heat capacity C is constant. There are three functional relations between the state variables of the gas, stating that the product of any two of them raised to some power depending on the polytropic index is constant. We have seen that the infinitesimal amount of heat Q transported in a polytropic process is given by the mass m of the gas times its generalized specific heat capacity C, times the infinitesimal change in its absolute temperature T. The total amount of heat Q transferred in the process is just the mass m times the generalized specific heat capacity C, times the difference between the final temperature T2 and the initial temperature T1 of the gas. The infinitesimal pressure volume work W done on the gas is given by minus the pressure P of the gas times the infinitesimal change in its volume V. The total amount of work W is equal to 1 over N minus 1, times the quantity of the final pressure P2 of the gas times its final volume V2 minus its initial pressure P1 times its initial volume V1. The infinitesimal change in the internal energy U of the gas is given by the mass m of the gas times its specific heat capacity Cv for a constant volume, times the infinitesimal change in its absolute temperature T. The total amount of change in the internal energy U is just the mass m times the specific heat capacity Cv, times the difference between the final temperature T2 and the initial temperature T1 of the gas. The infinitesimal change in the enthalpy H of the gas is equal to the mass m of the gas times its specific heat capacity Cp for a constant pressure, times the infinitesimal change in its absolute temperature T. The total amount of change in the enthalpy is given by the mass m times the specific heat capacity Cp, times the difference between the final temperature T2 and the initial temperature T1 of the gas. The second case we present the table is the isothermal process, where the polytropic index is equal to 1, and the absolute temperature T of the gas is constant. Here we have only one functional relation between the state variables of the gas, which is Boyle's law stating that the product of the pressure P and the volume V of the gas is constant. Since the temperature of the gas does not change in an isothermal process, the infinitesimal change in the heat Q is equal to the infinitesimal work W done on the gas. As a result, the total heat Q exchanged between the gas and its surroundings in an isothermal process is equal to the total work W done on the gas. The infinitesimal pressure volume work W done on the gas is given by minus the pressure P of the gas times the infinitesimal change in its volume V. The total amount of work W is equal to the mass m of the gas times its specific gas constant Rs times its absolute temperature T, times the natural logarithm of the ratio of the initial volume V1 of the gas to its final volume V2. By applying Boyle's law, we can express the ratio as the ratio of the final pressure P2 of the gas to its initial pressure P1. In isothermal processes the internal energy of an ideal gas does not change, therefore both the infinitesimal and the total change in the internal energy vanish. In an isothermal process, the enthalpy of an ideal gas does not change either. Then the infinitesimal and the total change in the enthalpy H vanish as well. The third type of thermodynamic process presented here is the isochoric process, where the polytropic index diverges, and the volume V of the gas is constant. The functional relation between the state variables is Gay-Lussac's law stating that the ratio of the pressure P of the gas to its absolute temperature T is constant. The infinitesimal amount of heat Q exchanged between the gas and the surroundings in an isochoric process is given by the mass m of the gas times its specific heat capacity Cv for a constant volume, times the infinitesimal change in its absolute temperature T. The total amount of heat Q transferred in the process is the mass m times the specific heat capacity Cv, times the difference between the final temperature T2 and the initial temperature T1 of the gas. Since the volume of the gas is constant in an isochoric process, the pressure volume work W done on the gas vanishes, that is the differential of the work W and the total amount of the work are equal to 0. The infinitesimal change in the internal energy U of the ideal gas is given by the mass m of the gas times its specific heat capacity Cv for a constant volume, times the infinitesimal change in its absolute temperature T. The total amount of change in the internal energy U is equal to the mass m times the specific heat capacity Cv, times the difference between the final temperature T2 and the initial temperature T1 of the gas. The infinitesimal change in the enthalpy H of the gas is given by the differential of the internal energy U, plus the volume V times the differential of the pressure P, which is equal to the mass m of the gas times its specific heat capacity Cp for a constant pressure, times the infinitesimal change in its absolute temperature T. The total amount of change in the enthalpy is given by the mass m times the specific heat capacity Cp, times the difference between the final temperature T2 and the initial temperature T1 of the gas. The next thermodynamic process presented here is the isobaric process, where the polytropic index diverges, and the volume V of the gas is constant. The functional relation between the state variables of the gas does not change, therefore both the infinitesimal and the total change in the internal energy vanish. The next thermodynamic process presented here is the next thermodynamic process is the isobaric process, where the polytropic index N vanishes, and the pressure P of the gas is constant. The functional relations between the state variables of the gas reduces to Charles' law stating that the ratio of the volume V of the gas to its absolute temperature T is constant. The infinitesimal amount of heat Q exchanged between the gas and the surroundings in an isobaric process is given by the mass m of the gas times its specific heat capacity Cp for a constant pressure, times the infinitesimal change in its absolute temperature T. The total amount of heat Q transferred in the process is equal to the mass m times the specific heat capacity Cp, times the difference between the final temperature T2 and the initial temperature T1 of the gas. The infinitesimal pressure volume work W done on the gas is given by minus the pressure P of the gas times the infinitesimal change in its volume V. The total amount of work W is equal to the pressure P of the gas times the difference between its final volume V2 and its initial volume V1. The infinitesimal change in the internal energy U of the ideal gas in an isobaric process is given by the mass m of the gas times its specific heat capacity Cv for a constant volume, times the infinitesimal change in its absolute temperature T. The total amount of change in the internal energy U is equal to the mass m times the specific heat capacity Cv, times the difference between the final temperature T2 and the initial temperature T1 of the gas. The infinitesimal change in the enthalpy H of the gas in an isobaric process is given by the differential of the internal energy U, plus the pressure P times the differential of the volume V, which is equal to the infinitesimal amount of the heat Q exchanged between the gas and the surrounding. The total change in the enthalpy of the gas can be written as the total change in the internal energy U of the gas, minus the total work W done on the gas, which is equal to the total amount of the heat Q exchanged between the gas and the surrounding. The last special case of the polytropic process is the adiabatic one, where the polytropic index is equal to the adiabatic index gamma, and there is no heat exchanged between the gas and the surroundings, that is the heat Q is equal to 0. Then the functional relations between the state variables of the ideal gas become Poisson's equations, stating that the product of any two of them raised to some power depending on the adiabatic index is constant. Since the exchange of the heat is forbidden between the gas and the surroundings, both the differential of the heat Q and the total heat Q vanish. As a result, the infinitesimal amount of pressure volume work W done on the gas, which is given by minus the pressure P of the gas times the infinitesimal change in its volume V is equal to the infinitesimal change in the internal energy U of the gas. The total amount of work W is given by 1 over gamma minus 1, times the quantity of the final pressure P2 of the gas times its final volume V2 minus its initial pressure P1 times its initial volume V1. This expression is equal to the total change in the internal energy U of the gas. The infinitesimal change in the internal energy U of the ideal gas in an adiabatic process is given by the mass m of the gas times its specific heat capacity Cv for a constant volume, times the infinitesimal change in its absolute temperature T. The total amount of change in the internal energy U is equal to the mass m times the specific heat capacity Cv, times the difference between the final temperature T2 and the initial temperature T1 of the gas. The infinitesimal change in the enthalpy H of the gas in an adiabatic process is given by the mass m of the gas, times its specific heat capacity Cp for a constant pressure, times the infinitesimal change in its absolute temperature T. The total amount of change in the enthalpy is given by the mass m times the specific heat capacity Cp, times the difference between the final temperature T2 and the initial temperature T1 of the gas. Now we present an important thermodynamic process called Carnot cycle, which is a theoretical model describing the thermodynamic cycle converting heat to work in steam engines. When we introduced the concept of thermodynamic cycle, we defined it as a connected sequence of thermodynamic processes, where the initial state of the first process and the sequence is the same as the final state of the last process in the sequence. As an illustration, we also showed the state space of the system where the thermodynamic cycle takes place. In the state space spanned by the axes of the state variables x1, x2, ellipsis, xn, the intermediate states of the thermodynamic cycle are represented by the points p1, p2 and p3. These states are connected with the path calligraphic p in the state space, which represents the cycle. We started the historical remarks on the concept of thermodynamic system with Nicolas Leonard Sadi Carnot, who studied steam engines to improve their performance in the conversion of a given amount of heat to mechanical work. In his book published in 1824, Carnot defined a theoretical heat engine shown in the cross-sectional diagram, where he considered the body of the water vapor or the working substance as an ideal gas in the cylindrical vessel of the steam engine with a frictionless piston, and the bodies A and B of constant temperature, which are the thermal reservoirs or baths brought into contact with the cylinder. He examined the thermodynamic cycle taking place in such a system, which is called Carnot cycle. Carnot cycle consists of 4 thermodynamic processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. We label the processes with the numbers from 1 to 4, starting with the isothermal expansion of the working substance. Since Carnot cycle is a sequence of idealized thermodynamic processes, all of them are supposed to be quasi-static. This means the following. The ideal gas law holds throughout the cycle, and the difference delta P between the internal pressure in the cylinder and the external pressure in the surroundings is small. In other words, the ratio of the magnitude of delta P to the external pressure is much smaller than 1. Similarly, the difference delta T between the temperature of the gas and the temperatures of the heat baths is also small, that is, the ratio of the magnitude of delta T to the temperatures of the heat baths is much smaller than 1. Now we examine all the 4 processes in Carnot cycle. The first process in the cycle is an isothermal expansion of a given amount of ideal gas in the cylinder, which is brought into contact with a heat reservoir of the absolute temperature T1. After the gas reaches thermal equilibrium with the reservoir, its absolute temperature becomes T1. The pressure PA and the volume VA of the gas at the absolute temperature T1 are the initial state variables of the gas in its initial state denoted by the letter A. If the external pressure is somewhat smaller than the pressure of the gas in the cylinder, the gas will undergo a quasi-static isothermal expansion. Then the initial volume VA of the expanding gas increases to the volume VB when it reaches its final state of the isothermal expansion denoted by the letter B. At the same time, its initial pressure PA drops to the pressure PB, while its absolute temperature T1 remains the same. During its isothermal expansion, the gas absorbs the heat Q1, and does the pressure volume work W'1 on the surroundings. We can illustrate the quasi-static isothermal expansion of the gas in the pressure volume diagram, where the family of the rectangular hyperbolas represent the isotherms of the given amount of ideal gas in the cylinder. Let us suppose that one of the isotherm represents the isothermal process of the gas at the absolute temperature T1. Then the initial state A and the final state B of the gas undergone the isothermal expansion lie on this isotherm, and the process is represented by the green curve on the hyperbola between the points A and B. The arrow indicates the direction of the process pointing from its initial state A to its final state B. We can calculate the heat Q1 absorbed by the gas during its isothermal expansion. Since the temperature of the gas is constant, its internal energy does not change in the process. Then the first law of thermodynamics states that the heat Q1 is equal to the work W'1 done by the gas, which can be written as the mass m of the gas, times its specific gas constant Rs, times its absolute temperature T1, times the natural logarithm of the ratio of its final volume VB to its initial volume VA. Since the final volume of the expanding gas is greater than its initial volume, the heat Q1 and the volume W'1 are positive. The second process in Carnot cycle is an adiabatic expansion of the gas in the cylinder. Here the gas in the cylinder is thermally insulated, preventing the exchange of heat between the gas and the surroundings. If the external pressure is still somewhat smaller than the pressure PB of the gas, then the gas will undergo an quasi-static adiabatic expansion. Since the expanding gas cannot absorb heat, it will cool down and its absolute temperature T1 drops to the absolute temperature T2 in the final state of the adiabatic expansion denoted by the letter C. The initial volume VB of the expanding gas increases to the final volume VC, whereas its initial pressure PB reduces to the final pressure PC. The expanding gas does the pressure volume work W'2 on the surroundings. In the pressure volume diagram, the adiabatic expansion of the gas is represented by a path along an adiabat passing through the point B. The adiabat depicted with the yellow curve is steeper than the isotherm of the absolute temperature T1, intersecting the adiabat in the point B. The path of the adiabatic expansion is represented by the orange color curve running between the initial state B and the final state C of the process. The arrow indicating the direction of the process points from the point B to the point C. The final state C of the gas lies on another isotherm of the absolute temperature T2, which is smaller than the initial temperature T1 of the gas. Since there is no heat exchange between the gas and the surroundings during the adiabatic expansion of the gas, the first law states that the pressure volume work W'2 done by the gas is equal to the change in its internal energy, which can be written as the mass m of the gas, times its specific heat capacity CV for a constant volume, times the difference between its initial temperature T1 and its final temperature T2. The work W'2 is also positive, due to the fact that the initial temperature of the cooling gas is greater than its final temperature. After the isothermal and the adiabatic expansion of the gas, the next two processes in Carnot cycle apply compression so that the gas could be brought into its initial state. The third process in the cycle is an isothermal compression of the gas, where the gas is brought into contact with the heat reservoir of the absolute temperature T2. Since the temperature T1 is greater than the temperature T2, the heat bath used in the first process, that is in the isothermal expansion of the gas, is also called hot reservoir, whereas the heat bath used in this process is called cold reservoir. If the gas remains in thermal equilibrium with the cold reservoir, then its temperature is constant during the process, that is, the absolute temperature of the gas is equal to T2. Now the state C is the initial state of the gas in the compression, and its pressure Pc and volume Vc at the absolute temperature T2 are the initial state variables of the gas. We can compress the gas in a quasi-static process by moving the piston slowly enough. Then the initial volume Vc of the gas is reduced to the volume Vd when it reaches its final state denoted by the letter D. At the same time, its initial pressure Pc increases to the pressure Pd, while its absolute temperature T2 remains the same. Here we suppose that the final state D of the gas is such a state, which allows the gas to return to the state A in an adiabatic compression. During its isothermal compression, the gas releases the heat minus Q'2 to the cold reservoir, where Q'2 is positive. The minus sign indicates that the heat flows out from the gas, extracting energy from the system. The moving piston does some work on the gas, that is the pressure volume work W'3 done by the gas on the surroundings is negative. In the pressure volume diagram, the initial state C and the final state D of the gas undergone the isothermal compression lie on the isotherm of the absolute temperature T2, and the process is represented by the purple curve on the hyperbola between the points C and D. The arrow on the curve points from the state C to the state D, which is the opposite direction of the isothermal expansion between the states A and B. We can calculate the heat Q'2 released by the gas during its isothermal compression. From the first law of thermodynamics we obtain that minus the heat Q'2 is equal to the work W'3 done by the gas, because the internal energy of the gas remains constant. The work can be written as the mass m of the gas, times its specific gas constant Rs, times its absolute temperature T2, times the natural logarithm of the ratio of its final volume Vd to its initial volume Vc. Since the initial volume of the compressed gas is greater than its final volume, minus the heat Q2 and the work W'3 are negative. The last process in Carnot cycle is an adiabatic compression of the gas. Here the gas in the cylinder is thermally insulated as in the case of its adiabatic expansion, and there is no exchange of heat between the gas and the surroundings. If we compress the gas by moving the piston slowly enough, then the gas will undergo a quasi-static process. Since the gas cannot release heat during its compression, it will warm up, and its absolute temperature T2 increases to the absolute temperature T1 in the final state of the process, which is the initial state A of the cycle. During the compression, the initial volume Vd of the gas decreases to the volume Va, whereas its initial pressure Pd increases to the pressure Pa. At the same time, the pressure volume work W'4 is done by the gases minus the work done on the gas by the moving piston. As already mentioned, the choice of the state D of the gas is such that the adiabat passing through it also passes through the state A, which is depicted by the yellow curve connecting these states in the pressure volume diagram. Therefore, the adiabatic compression of the gas is represented by a blue color path along this adiabat between its initial state D and its final state A. The direction of the process is the opposite of the direction of the adiabatic expansion of the gas, as indicated by the arrow. There is no heat exchange between the gas and the surroundings during the adiabatic compression of the gas. As a result, the first law reduces to the equation stating that the pressure volume work W'4 done by the gas is equal to the change in its internal energy, which can be written as the mass m of the gas, times its specific heat capacity Cv for a constant volume, times the difference between its initial temperature T2 and its final temperature T1. This is equal to minus m times Cv times the difference between T1 and T2. The work W'4 is negative, since the final temperature T1 is greater than the initial temperature T2 for the warming gas. After determining the work done in each process, we can compute the net work done in Carnot cycle. The net work W' done by the gas is simply the sum of the work done in each process, that is the work W'1 and the work W'2 done by the system during the expansion of the gas, and the work W'3 and the work W'4 done by the system during the compression of the gas. The work done during all the four processes of the cycle will be shown in this table. In the first process, where the gas is brought from the state A to the state B in an isothermal expansion at the absolute temperature T1, the work W'1 is equal to the mass m of the gas, times its specific gas constant Rs, times its absolute temperature T1, times the natural logarithm of the ratio of its final volume Vb to its initial volume Va. This work done by the expanding gas is positive. In the second process, where the gas is brought from the state B to the state C in an adiabatic expansion, the work W'2 is given by the mass m of the gas, times its specific heat capacity Cv for a constant volume, times the difference between its initial absolute temperature T1 and its final absolute temperature T2. This work done by the expanding gas is positive. In the third process, where the gas is brought from the state C to the state D in an isothermal compression at the absolute temperature T2, the work W'3 is equal to the mass m of the gas, times its specific gas constant Rs, times its absolute temperature T2, times the natural logarithm of the ratio of its final volume Vd to its initial volume Vc. Since the gas undergoes a compression, the work W'3 done by the gas is negative. In the fourth process, where the gas is brought from the state D to the state A in an adiabatic compression, the work W'4 is given by minus the mass m of the gas, times its specific heat capacity Cv for a constant volume, times the difference between its final absolute temperature T1 and its initial absolute temperature T2. Since the gas undergoes a compression, the work W'4 done by the gas is negative. Here we can see that the work W'2 done in the adiabatic expansion is equal to minus the work W'4 done in the adiabatic compression. Therefore, they cancel each other out in the sum. As a result, the net work W' done by the system is equal to m times Rs times T1, times the natural logarithm of the ratio of Vb to Va, plus the m times Rs times T2, times the natural logarithm of the ratio of Vd to Vc. Since both terms in the sum are greater than 0, the net work W' is positive. Here we can use one of Poisson's equations derived for an adiabatic process in an ideal gas stating that the absolute temperature T of the gas, times its volume V raised to the adiabatic index gamma of the gas minus 1 is constant in the whole process. If we apply this equation for the adiabatic expansion of the ideal gas in Carnot cycle, then we can write that the initial absolute temperature T1 of the gas, times its initial volume Vb to gamma minus 1 is equal to its final absolute temperature T2, times its final volume Vc to gamma minus 1. Similarly, we can apply Poisson's equation for the adiabatic compression of the ideal gas in Carnot cycle. Then we state that the final absolute temperature T1 of the gas, times its final volume Va to gamma minus 1 is equal to its initial absolute temperature T2, times its initial volume Vd to gamma minus 1. If we express the ratio of the absolute temperature T1 to the absolute temperature T2 from these equations, we obtain the following equations. First, this ratio is equal to the ratio of Vc to Vb raised to gamma minus 1. Second, this ratio is also equal to the ratio of Vd to Va raised to gamma minus 1. As a result, the expressions in the right-hand side of these equations are equal, and we can write that the ratio of the volume Vc to the volume Vd is equal to the ratio of the volume Vd to the volume Va. Therefore, the ratio of the volume Va to the volume Vb is equal to the ratio of the volume Vd to the volume Vc. Now we can substitute this result into the net work W' done by the gas, which gives m times Rs times T1, times the natural logarithm of the ratio of Vb to Va, plus the m times Rs times T2, times the natural logarithm of the ratio of Va to Vb. Since the logarithm of a fraction is equal to minus the logarithm of the reciprocal of that fraction, we can write the right-hand side as m times Rs, times the difference between T1 and T2, times the natural logarithm of the ratio of Vb to Va. This expression is also equal to m times Rs, times the difference between T1 and T2, times the natural logarithm of the ratio of Vd to Vc, which shows that in order to determine the net work W' done in Carnot cycle, we can use the initial and the final volume of the gas either in the isothermal expansion or the isothermal compression of the cycle. We can also obtain the work done in the whole Carnot cycle by evaluating the pressure-volume integral from the area of its graph in the pressure-volume diagram. The pressure-volume work W' done by the gas in the whole cycle is given by the contour integral of the pressure P of the gas as a function of its volume V with respect to the volume V along the path of Carnot cycle. In the pressure-volume diagram, the path is represented by the closed curve connecting the points A, B, C and D. The contour integral along this path is equal to the area of the plane figure defined by this closed curve. It is easy to show that W' is given by this area, if we split the contour integral to the terms of each process in the cycle. In the first process represented by the curve connecting the points A and B in the pressure-volume diagram, the work W'1 done by the system is equal to the integral of the pressure P with respect to the volume V from the initial volume Va of the system to its final volume Vb. This integral is equal to the green area of the plane figure under the curve connecting the points A and B. Similarly, In the second process represented by the curve connecting the points B and C, the work W'2 done by the system is equal to the integral of the pressure P with respect to the volume V from the initial volume VB of the system to its final volume VC. This integral is equal to the blue area of the plane figure under the curve connecting the points B and C. The total work done by the two processes is the sum of the work W'1 and the work W'2. Since the direction of the integration along these two curves indicated by the arrows is positive, the integrals, that is the areas under the curves, are also positive. As a result, the total work done in these processes is positive. Now we consider the second two processes in Carnot cycle. In the third process represented by the curve connecting the points C and D in the pressure volume diagram, the work W'3 done by the system is equal to the integral of the pressure P with respect to the volume V from the initial volume VC of the system to its final volume VD. This integral is equal to the blue area of the plane figure under the curve connecting the points C and D. Similarly, in the fourth process represented by the curve connecting the points D and A, the work W'4 done by the system is equal to the integral of the pressure P with respect to the volume V from the initial volume VD of the system to its final volume VA. This integral is equal to the green area of the plane figure under the curve connecting the points D and A. The total work done in the two processes is the sum of the work W'3 and the work W'4. Since the direction of the integration along these two curves indicated by the arrows is negative, the integrals, that is the areas under the curves, are also negative. As a result, the total work done in these processes is negative. Since the total area obtained in the first two integrals is positive and the total area obtained in the second two integrals is negative, we can conclude the following. The net pressure volume work W' done by the system in Carnot cycle is given by the difference between the total area of the two plane figures under the curve connecting the points A, B, and C and the total area of the two plane figures under the curves connecting the points C, B, and A. This difference is simply equal to the area of a plane figure defined by the closed curve connecting the points A, B, C, and D. We can also interpret the work W' done in the whole cycle as a function of a set of parameters characterizing the cyclic process. By applying the first law of thermodynamics, we can immediately see that the work done in a thermodynamic cycle is always equal to the heat exchanged between the system and the surroundings, since the internal energy of the system is the same in its initial and its final states. That is, the work W' done by the system is equal to the heat Q1 absorbed by the expanding gas minus the heat Q'2 released by the gas during its compression. Therefore the heat Q1 and the heat Q'2 completely determine the work done by the gas in Carnot cycle. However, other parameters describing the process are more convenient to measure. We have shown that the work W' done in the whole cycle is also equal to the mass m of the gas times its specific gas constant Rs, times the difference between the maximum absolute temperature T1 and the minimum absolute temperature T2 of the gas, times the natural logarithm of the ratio of the final volume VB of the gas to its initial volume VA and its isothermal expansion. In this case, the mass m of the working substance together its specific gas constant Rs are determined by the given amount of water vapor used in the steam engine. Another parameter chosen by the design of the engine is the difference between the maximum and the minimum temperatures in the cycle, which are determined by the hot and cold reservoirs brought into contact with the working substance. Finally, the ratio of the final volume of the working substance to its initial volume in the isothermal compression is also a parameter, which can be determined by the geometry of the cylinder in the moving piston of the steam engine. We can also apply a symbolic notation for the exchange of energy between the system and the surroundings in Carnot cycle, which indicates the direction of the transport of energy in the pressure-volume diagram. In the first process, where the gas undergoes an isothermal expansion between the states A and B, the expanding gas absorbs the heat Q1, which can be represented by an arrow pointing inside the plane figure defined by the closed curve connecting the points A, B, C, and D. Its direction indicates that the heat Q1 absorbed by the gas contributes to the internal energy stored in the system. The work W'1 done by the expanding gas reduces the internal energy of the system, which is indicated by the arrow pointing outside the closed curve representing the path of the cycle. In the second process, where the gas undergoes an adiabatic expansion between the states B and C, there is no exchange of heat but the expanding gas still does the pressure-volume work W'2, which reduces the internal energy of the system. Therefore the arrow representing the work W'2 points outside the closed curve connecting the points A, B, C, and D. In the third process, where the gas undergoes an isothermal compression between the states C and D, the gas releases the heat Q'2, which is represented by an arrow pointing outside the plane figure defined by the points A, B, C, and D. Its direction indicates that the heat Q'2 released by the gas reduces the internal energy of the system. The negative work W'3 done by the gas during its compression increases the internal energy stored in the system, which is indicated by the arrow pointing inside the plane figure. In the fourth process, where the gas undergoes an adiabatic compression between the states D and A, there is no exchange of heat but the gas does the negative pressure volume work W'4, which increases the internal energy of the system. Therefore the arrow representing the work W'4 points inside the closed curve connecting the points A, B, C, and D. We have seen that the work W'2 and the work W'4 have the same magnitude but the opposite sign. Therefore the arrows W'2 and W'4 have the same length, but the first one points outside the closed curve and the second one points inside the closed curve. As a result, they cancel each other out. Only the work W'1 and the work W'3 contribute to the net work W', which is produced by the conversion of the net heat Q1 minus Q'2 exchanged between the system and the surroundings. Now we can summarize the process of conversion of energy by a steam engine operating in Carnot cycle. In Carnot cycle, the water vapor absorbs the heat Q1 from a boiler, which is a hot source at the absolute temperature T1, and releases the heat Q'2 to a condenser, which is a cold sink at the absolute temperature T2, and is the net work W'. The thermal efficiency eta of Carnot cycle is defined by the ratio of the useful work W' to the heat Q1 delivered from the boiler. Since the heat Q1 is equal to the work W'1 done by the body of the water vapor during its isothermal expansion, we can write that eta is equal to W' divided by W'1. We have already determined the quantities in the numerator and the denominator of the fraction. Then we can write that eta is equal to the mass m of the water vapor, times its specific gas constant Rs, times the difference between the temperature T1 and the temperature T2, times the natural logarithm of the ratio of the final volume Vb of the vapor to its initial volume Va during its isothermal expansion, divided by m times Rs times T1, times the natural logarithm of the ratio of Vb to Va. By simplifying this expression, we obtain T1 minus T2, divided by T1, or 1 minus the ratio of T2 to T1. Then we can conclude that the thermal efficiency of a steam engine only depends on the temperature of its boiler and its condenser. The higher the absolute temperature T1 of the boiler and the lower the absolute temperature T2 of the condenser, the greater thermal efficiency of Carnot cycle is. The maximum value of eta is equal to 1, where we have 100% thermal efficiency. In such a case, the heat Q1 delivered by the hot reservoir is completely converted into the mechanical work W' without any loss, that is the heat Q'2 vanishes. However, the formula for eta implies that 100% thermal efficiency would be possible only if the condenser or the cold reservoir were at absolute zero, that is the temperature T2 were equal to 0 Kelvin. In fact, it is impossible from both practical and theoretical reason and the value of eta is always less than 1. As a result, in Carnot cycle converting the heat into work with some loss, only a fraction eta times Q1 of the heat Q1 delivered by the boiler or the hot source can be converted into the work W'. The rest of it, which is equal to 1 minus eta times Q1 is released to the condenser or the cold reservoir. We have seen that Carnot cycle is an idealized thermodynamic cycle of steam engines. Carnot cycle can also be considered as a model of a heat engine, which converts the heat Q1 delivered by the boiler or the hot source into the work W', while the heat Q'2 is released to the condenser or the cold sink as a loss of heat. Although the operation cycle of real heat engines is not exactly a Carnot cycle, the thermal efficiency introduced in this model is not merely a quantity describing a conversion of energy in a theoretical process. It plays a crucial role in thermodynamics, since we will demonstrate that eta, which is equal to the difference between the absolute temperature T1 of the hot source and the absolute temperature T2 of the cold sink divided by T1, provides the maximum of the thermal efficiency of any kind of heat engine. We can also reverse the direction of Carnot cycle, where the cycle is performed through the thermodynamic states A, D, C, B, and again A. In the processes between the states A and D, and between the states D and C of the reversed Carnot cycle, we apply an external pressure somewhat less than the pressure of the gas in the cylinder. In the processes between the states C and B, and between the states B and A, we use an external pressure somewhat greater than the pressure of the gas. As a result, we only change the sign of the heat exchanged and the work done in the cycle, that is, we reverse the direction of the transport of energy in the process. In the reversed Carnot cycle, the gas absorbs the heat Q'2 from the condenser and releases the heat Q1 to the boiler, while external forces do the work W on the gas, which is equal to minus W'. Such a reversed process has two different applications. The first one is the heat pump used to control temperature in enclosed spaces by heat transfer. A heat pump extracts the heat from its colder surroundings at the absolute temperature T2 and transfers it into a warmer place held at the absolute temperature T1 by using the external work W. We describe the efficiency of this process with the coefficient of performance denoted by COP with the subscript H, that is heating, which is defined by the ratio of the magnitude of the heat Q1 to the magnitude of the work W'. This fraction is equal to the absolute temperature T1 divided by the difference between the absolute temperatures T1 and T2. The second type of application for the reversed cycle is the refrigerator, which removes the heat from the place held at the absolute temperature T2, and transfers it to its warmer surroundings at the absolute temperature T1 by using the external work W. We denote the coefficient of performance for refrigerators by COP with the subscript C, that is cold, and define it by the ratio of the magnitude of the heat Q'2 to the magnitude of the work W', which is equal to the absolute temperature T2 divided by the difference between the absolute temperatures T1 and T2. In the end of this presentation on quasi-static processes in ideal gas, we will give a summary of the topics discussed here. We started with the classification of thermodynamic processes based on the criteria fixing one of thermodynamic or path variables of the system during the process. We enlisted three different classes of processes which were already presented in the discussion on ideal gas law. These were isothermal processes where the temperature of system is constant, isochoric processes where the volume of the system is constant, and isobaric processes where the pressure of the system is constant. We also talked about two further classes, such as adiabatic and polytropic processes. Both of them use criteria related to the exchange of heat between the system and the surroundings. In the case of adiabatic processes, this heat transfer is zero, whereas in polytropic processes the exchange of heat is proportional to the change in the temperature of the system. The first class of thermodynamic processes discussed here was the quasi-static isothermal process in a given amount of ideal gas. By applying the first law of thermodynamics, we could demonstrate that the total amount of heat absorbed by the gas is converted to the work done by the gas. We also determined the heat absorbed and the work done by the gas as functions of the thermodynamic variables of the gas in its initial and final states. The next class of thermodynamic processes presented here was the quasi-static isochoric process in a given amount of ideal gas. By applying the first law, we could demonstrate that the total amount of heat absorbed by the gas increases its internal energy. We also determined the heat absorbed by the gas and the change its internal energy as functions of the thermodynamic variables of the gas in its initial and final states. The third class of thermodynamic processes discussed here was the quasi-static isobaric process in a given amount of ideal gas. By applying the first law, we could demonstrate that the total amount of heat absorbed by the gas increases its enthalpy. We also determined the heat absorbed by the gas and the change its enthalpy as functions of the thermodynamic variables of the gas in its initial and final states. We also introduced the thermal efficiency of a thermodynamic process as converting heat into work, and determined it for an isobaric process in an ideal gas. Besides the classes of well-known thermodynamic processes from the presentation on ideal gas law, we considered a further class, namely the quasi-static adiabatic process in a given amount of ideal gas. By applying the first law, we could demonstrate that the total work done on the gas increases its internal energy. We also determined the functional relations between the thermodynamic variables of the gas, known as Poisson's equations. We analyzed one of Poisson's equations describing the relation between the pressure and the volume of the ideal gas, and found that the slope of the adiabat is greater than the one of the isotherm passing through the same thermodynamic state. We introduced the adiabatic compressibility for gas as well and determined the speed of sound in adiabatic approximation. The last class of thermodynamic processes presented here was the quasi-static polytropic process in a given amount of ideal gas. By applying the first law, we determined the functional relations between the thermodynamic variables of the gas in such a process. We demonstrated that the isothermal, isochoric, isobaric and adiabatic processes are special cases of the polytropic process. We also derived several functional relations between the heat exchanged and the work done in the process. The pressure-volume work was computed, and the explicit form to the heat flux together with the changes in the internal energy and the enthalpy of the gas were given as well. All these findings were summarized in a table for all the classes of thermodynamic processes treated here. We finished the presentation with a discussion on Carnot cycle, the theoretical model of the operation cycle of a steam engine. We saw that Carnot cycle is a sequence of 2 isothermal and 2 adiabatic processes, which we discussed in more detail. The heat exchanged and the work done were determined in each process, which allowed us to provide the total heat exchanged and the total work done in the whole cycle. We also introduced the concept of heat engine as a theoretical model describing the conversion of heat into mechanical work, and defined the thermal efficiency of Carnot cycle in heat engines. Reversed Carnot cycle was discussed as well, and we presented 2 types of engines with this operation cycle, such as heat pumps and refrigerators.